IIT Bombay. It's a great pleasure to have Linquan Ma from Purdue University. Linquan studied at Michigan under Professor Hochster, and then he spent a few years at Utah. In fact, I met him in 2016. And since then, we have had pleasure of reading many remarkable papers by him. In fact, in our department, we ran a workshop on his thesis where he solved Lex conjecture in dimension 3. And I think we might see the whole solution very soon. So it's a great pleasure to have Linquan in our seminar, and you may start now.
Okay, and thank you very much for the introduction, and it's my great pleasure to speak. So today I'm talking about the deformation problem for F-injective singularity. Since I thought so when I was informed, so this seminar is about mainly about characteristic P method, and so I want to give a topic that I have been working on for many years, but without too much success on this one. But it's I think it's a very interesting question, and it's I think I encouraged like some young mathematician maybe to solve it soon. Okay, so throughout my talk, R is a Rm. I'm going to always use this notation. It's a commutative Noetherian and local ring with multiplicative identity 1 that I always going to assume is characteristic P. And m, little m, is the unique maximum ideal, and D is always the dimension of the ring. Okay, so let me first recall that, so under this setup, we have the Frobenius map. It's just sending little r to the p, right? So this is the Frobenius. And what's important is that this is a ring homomorphism. Right, so this is it's both additive and multiplicative, so this requires the ring to contains the finite field. Okay, so and of course I can also iterate this, so the eth Frobenius map, right? And this all these will be ring homomorphism. And second, let me briefly recall the local cohomology. So I take an ideal, let's say find an ideal I, say I pick some generators x1, xn. So this is an ideal of R, right? So then I can look at the local cohomology module supported at I. So hi little I of R. So let me remind you, so there are a bunch of ways you can define this local cohomology, but for this talk, or there's one very convenient way is to just use the check complex. This is the ith cohomology of the check complex. Right, and so the last term is okay. All right, so this is the check complex. And so remember, we have a Frobenius map on R that I just said here. And clearly, this Frobenius map passes to the localization. So for each of this localization, you have a Frobenius. All right, so basically, the Frobenius induces a map on the entire check complex. So it induces a map on the cohomology of the check complex. So in other words, so there's a natural induced action on the local cohomology of R supported at any ideal, and you can just view it this way. Okay, so again, the Frobenius induces a map on each of the localizations, so it induces a map on the check complex. So take cohomology, it induces a map on the local cohomology. And so just for the convenience of the talk and the theorem that I'm gonna prove later. So so alternatively, you can also view this map on local cohomology as just the map induced by the Frobenius. Well, okay, what I mean. So recall that whenever I have a ring homomorphism, that if R2S is any ring homomorphism, right? So then it induces a map from HII of R to HISI of S. Okay, and so you can let me just so the Frobenius map or the Frobenius action on the local cohomology module can be viewed as like is induced by the ring homomorphism like the Frobenius map. All right, so just as I said, this is a ring homomorphism, so it induces a map on local cohomology, and the I, right? So I mean the I, if you expand it to the right-hand side, it gives like I to the bracket P, but the local cohomology only matters the about the radical, so you can identify the right-hand side as the HII of R. Okay, so it's just a few. I mean, there's a bunch of ways you can understand the Frobenius action on the local cohomology. I just want to emphasize this because this plays a crucial role in the talk. All right, and so now with this set up, so let me give you a bunch of definitions. So first, Rm is called F split if the Frobenius map splits as a map of R modules. Right, so this is the R on the left-hand side. Okay, so you just view this as a ring homomorphism, and I want this map to be, if I view everything as a module over the left-hand side copy of R, I want this map to be split. So that's the definition of F split. And two, R is called F-injective if the induced Frobenius action each local cohomology module supported at the maximal ideal is injective. This is for all R. All right, and so these are the two definitions that I will be working on. I'm sure you have seen this maybe in some other people's talk, but I just want to point it out. As a remark that so you might have people or like maybe more often to use the word F pure. But at least in today's talk or in most of the contexts, the F pure and F split, you don't really have to distinguish them. So so I'm just gonna say, so first, under mild assumptions. So in particular, for example, when Rm is complete, right? So then the ring is F split if and only if the ring is F pure in whatever sense like you define. But I'm not going to define F pure in this talk because the F split is really the property that I'm going to use. And all the question that I'm going to interested at least will easily pass to the completion. So I don't really have to distinguish these two. So I won't define this because it's slightly more technical than F-split, but in most contexts, it's really the same thing. So I'm just going to work with F-split rings. And two, F-split, or if you like F-pure, whatever that means, this clearly implies F-injective. Okay, so this is it's not hard to prove in the general context, but at least if you're assuming if you are willing to assume your ring is F-split, then it sort of obviously implies F-injective, because you can one way, for example, you can use this viewpoint, right? So if you have a ring homomorphism that is split, then of course the induced map on local cohomology also split. So in particular, the induced map on local cohomology would going to be injective. So from this point of view, it's very obvious that F-split implies F-injective. Okay, so and now let me focus on this the deformation question. So this is the question that I'm gonna interested. So what did it say, right? So in the purely algebraic context, it says the following. So suppose X inside R is a non-zero. Oh, let me just say this is a regular element. So in other words, it's a non-zero divisor, and I'm gonna assuming the quotient ring R mod X is F-split or F-injective. Right. So then I ask myself, so then the question asks, is R itself F-split or F-injective? Okay, so this is the question. It's, as I said, the question is very simple to state. It doesn't really require any background on this topic to just understand this question, right? And so, of course, this question has some geometric meaning. If you have a sort of a family over a curve, and if you want one of the special fibers, whatever, F-split or F-injective singularities, then the question is really whether the fibers near that special fiber has whatever singularities that you expect. But anyway, so I want to focus on the algebraic side. So this is the purely algebraic formulation of the deformation question. Okay, and so now, first of all, well, there have been a lot of work actually on this question. So first of all, for F-split, the answer is no, unfortunately. Okay, so I think the first counterexample is given by Feder, which in his famous paper, this F purity and rational singularity, he gave the first example that you have a quotient by a non-zero divisor, which is F pure or F split, but the ring itself is not F pure or F split, right? So he gave the first counter, but I think his example only works in some small characteristic. But then I think well, at least this is, I mean, I think maybe this is well known, but I think the first example that I learned from this is due to Anurag Singh. He gave a counterexample in 1999, and then it works in arbitrary, and it's actually very simple. So let me just maybe mention this example even. Let's go to Singh. Is the
Linquan, there is a question.
Right. I'm reading that.
Yeah,
Is the
I'll relay the
converse
question. Yeah.
No, unfortunately, the converse is not true. So if R is F pure or F split, it's or F split F injective, it's very hard to say about general hypersurface. For example, even if R is regular, right? So you can take a hypersurface which is arbitrarily bad singularity. So you can expect the special fiber or whatever to have the singularities you like. Okay, so let me just mention the analog things example. So you take Rm to be K double bracket XY ZT, and you go modulo XY YZ ZX minus T squared. Okay, and so then if you look at the quotient R mod T, T is a non-zero divisor. You can check this. That's just isomorphic to a Stanley Reisner ring, XYZ modulo XY YZ ZX. This is F split. This is a regular ring mod square free monomial ideal, so it's F pure. But you can check. For example, in this case, at least in small characteristic, you can just use Macaulay 2 and Feder's criterion. I hope somebody mentioned this Feder's criterion, but if not, it's some criterion of like determining whether the ring is F pure in terms of the defining equation is very explicit, right? So you can check this that the ring itself is not F split. Okay, so it's a very simple example. So this is basically the status for F split singularity. So unfortunately, the answer in general is no, but it's true. Oh, maybe I should say it's okay if R is Gorenstein. Right. So, but in the Gorenstein case, F pure or F split is just equivalent to F injective. So that basically leads to the natural question of whether F injective always satisfies this conclusion of the deformation question. But for F injective, this question is open. In general. Okay, and so today the rest of the talk, I'm gonna focus on the question, and I'm gonna report some partial progress on this question. Right, so the question now is just, if I have a local ring of characteristic P and suppose have a non-zero divisor such that R mod X is F injective, and then I wanted to know whether R itself is F injective.
The characteristic is in any prime number in Anurag Singh's example?
Correct. So K is arbitrary. So K is characteristic P for any P.
Yeah.
Right. And there are other examples. I think he gave a lot, but I take the simplest one in Singh's paper. Characteristics of singularity. Oh, okay. Yeah, thank you. Yeah, just please remind me if I'm looking at the chat, but if I didn't get there, so you can just interrupt me. Okay, so now the main theorem that I'm gonna tell you today. So again, the usual is the assumption X is a regular element. If either one of the following is, if either let me say 1, R is co-Macaulay, and R mod X is F injective, or R mod X is F split, Okay. So then R is F-injective. Okay, so the general question asked like R mod X is F-injective, whether that implies R is F-injective. And so now the first part of the theorem says, well, we don't know whether this is true in general, but it's true if you put the Cole-Macaulay assumption on the ring. Okay, and the second part is maybe more interesting. It said, okay, remember, so Singh's counterexample says, if R mod X is F split, R may not be F split, right? So in this example, but the part 2 said if R mod X is F split, then R is at least F injective. It's not so far from F split. Okay, and so before I start the proof, let me just mention one is due to feather. Okay, of course, actually the proof is easy, but I will sketch below. And 2 is actually not is proven not so long ago. It's 2 is due to Oichi, Lance Miller, and Kazuma Shimomoto. This is in 2014, so it's sort of recent result, but anyway. So. All right, so, and well, there are some other sporadic cases that this question is known, but so far as my understanding, like these two are the most important case that the question has a positive answer. Okay. Okay, so let me sketch the proof of these two results. So let me first prove one, the Cole-Macaulay case. So the proof actually in this case is not difficult. So if R is Cole-Macaulay, right? So remember, our goal is to show R is F-injective, but if you remember the definition of F-injective, we want the Frobenius action on the local cohomology module supported the maximum ideal is injective. But since we assume R is Cole-Macaulay, there's only one local cohomology module, namely the top one, because the lower one, they vanish. Okay, so it's enough to show the induced Frobenius action on the top local cohomology module is injective. This is the only one you have to worry about because all the lower one, they're already zero, so there's nothing to check. Okay, and so, oops. So now I consider the following diagram. Okay. Right. So I write down the obvious short exact sequence on R, and now I want to observe that you can actually there's a compatible Frobenius action on this short exact sequence. So namely, I have Frobenius action on R, and that Frobenius action obviously induces the same Frobenius action on R mod X. Okay, just sending R to the P, and here just sending R bar to R bar to the P, whatever. So this diagram obviously commutes. All right, and so but here I have I want to say like I have an induced action here, but you have to be a little bit careful here, right? So if I put a natural Frobenius here, then this left square does not commute, right? And so if you want the left square to be commute, you should put inside here x to the p minus 1 times n. Right? So it's maybe I leave it to you as a simple exercise to check it. So if I first apply Frobenius and then I multiply by x to the p minus 1, then I make the left hand side diagram commute. So basically, because f to the x, if you apply Frobenius to x, I get x to the p. So that's why I have to put on this extra p minus 1 here. Okay. Okay, so now this diagram, right? So remember, every short exact sequence induces a long exact sequence in the local cohomology. So this induces a long exact sequence on local cohomology, but of course, now I only have to worry about the top one because the rings are chromocopic. The lower HMI, they all vanish. So I only need to look at the top one. Okay. And now I'm gonna keep track of what's happening down on the bottom line. I have to keep track of the Frobenius action. So here, right? So this is the natural Frobenius. And here is the natural Frobenius again, but in the middle, this middle column corresponds to what's happening on the left-hand side. I mean, this column here corresponds to this column. So I should put the Frobenius, but I'm composed with the x to the p minus 1. So x to the p minus 1 times capital F. Okay, so now I have a diagram like this, and my assumption, remember, is that R mod x is F-injective. And I wanted to show R itself is F-injective. That is, my assumption is that this map is injective, right? And I want to show this capital F on HMDR is F-injective, right? And what I'm gonna prove now is the slightly stronger statement that I'm actually gonna show the middle map is injective, right? So we'll show that x1 times F is injective on HMDR. Right, so this clearly implies F itself is injective because this is a composition of two maps, the Frobenius and multiplication by x to the p minus 1. So this is injective is certainly stronger than capital F itself. It's F injective. Sorry, it's injective. Okay. So now we just argue about contradiction. So if something is in the kernel, okay. So then we may assume eta is in the circle, right? Because for any element in the local cohomology, I can replace it by a multiple. Well, if eta is in the kernel, then all the multiples of eta is also in the kernel, and I can always replace eta by a multiple which is in the circle of the local cohomology. So I can always assume that, right? But if eta is in the circle, then x times eta equals to 0, right? Because let me just maybe put so I pick eta inside here, right? So since I'm assuming this maps to 0, right? But I can also assume eta is in the circle, so I can also assume eta maps to 0 here, right? But then tracing this diagram, since eta has a trivial image when you map to HMDR, when you multiply it by x, so eta is actually coming from here, okay? Because of the exact sequence. But then this eta has some image inside here. Let me call it maybe like theta here, right? So then you see that this commutative diagram tells you that theta maps to 0, but the bottom line is an exact sequence, so theta is 0. But if theta is 0, then eta is 0 because the left-hand side Frobenius is injected. Okay, so it's a very easy diagram tracing. So let me just conclude by words here. So if I pick eta is in the circle of HMDR such that it also lies in the kernel of this middle vertical map, right? So then x times eta is equal to 0. So then that basically shows eta comes from HMD minus 1 of R mod x. Okay, but this contradicts Okay, so contradicts with the injectivity of the Frobenius on HMD-1 R mod X. Okay, so that's the proof in the Cohen-Macaulay case. Okay. See any questions? Okay, great. And so for the rest of the talk, I have like maybe 20 minutes or slightly more than 20 minutes. So let me try to sketch the proof of 2. So assuming R mod X is F split, and I wanted to prove the same statement, I want to show like R is F injective. I'm not assuming any Cohen-Macaulay assumption this time, right? So you see, the question gonna become more involved because instead of only controlling the top local cohomology, you have to control all the lower local cohomology. Okay? And actually the argument for the top local cohomology doesn't like work as in the Cohen-Macaulay case because you don't have the injectivity here. I mean, it's not necessarily you have this injectivity here. So. Okay, so now let's see any questions. So to prove 2, we need the following result. This is proof in part of my thesis. So suppose this R is F split, right? Then for all F stable submodule, I'm gonna define this in a second. For all F stable submodule, inside the local cohomology module supported the maximum ideal, the induced Frobenius action on this quotient is injective. Okay. So let me just put a remark. Right. So each of the each of the local cohomology module. Well, the thing I'm going to interested is the local cohomology supported at the maximum ideal. But in any case, each of this local cohomology module has a natural Frobenius action, as I just I sketched at the beginning of the talk. So here I have a natural Frobenius, and R submodule N is called F stable. Means if I consider the natural Frobenius action, it sends N to itself. Just what you imagine it should be. So Fn is inside N. Okay, so where this capital F is the natural Frobenius action on the local cohomology model. Okay, so that's what I mean by F stable. So for example, what are F stable? So for example, the local cohomology, the whole module itself, right? So this module itself is a trivial F stable submodule, and also the 0 module is always F stable, right? Because F0 is 0, so the 0 module is always F stable. So basically the conclusion of this, if you think about this theorem, the conclusion is much stronger, or at least stronger than saying the Frobenius action on HMIR itself is injective, right? So if you take N to be 0, then it's precisely saying the Frobenius action on HMIR itself is injective. That's F injective condition. But the theorem says if R is F split, then you have this, slight stronger assumption that not only the Frobenius is injective on HMIR, but it's actually injective after a quotient out by any F stable submodule of HMIR. Okay. So I'm going to sketch a proof of this. Right. So first, we claim the following. So there's a claim. So I let R R2S be a ring homomorphism that is split. Okay. And let's say eta inside HMIR and N inside HMIR is a submodule. Okay, and so the claim is that, so suppose the image of eta in this HM, well, remember a ring homomorphism induces a map on the local cohomology. So suppose the image of eta inside the HMIS is contained in the S span of the image of this N, this submodule N in HMSIS. So the image of N is an R submodule. So the image of N inside this HMIS, it may not be an S submodule, but I just look at the span of all these, just look at the S span of that image. That's going to be an S submodule. So suppose the image of eta is in the S span of the image of N. So then I want to conclude eta is contained inside it. Okay. So that's the claim. Let's try to, oops, sorry. I don't want to. So the proof is very simple. Actually, you just need to realize some sort of obvious diagram commutes. So the only, well, of course, this claim is false in general. If I just look at an arbitrary ring homomorphism, there's no reason that the image is in the in the induced the image in the span implies something. So the only condition here is that the ring map is split. So I have to use the splitting really. Okay, and so I let phi S to R be a splitting. Right, so that is if I compose R with compose this map with, so I mean, what does that mean? That means this is an R linear map. And if I compose this with the natural map from R to S, I got the identity map on R. In particular, this map sending 1 to 1. Right, so it's 1 to 1. All right, so, and now the only thing that I have to really think a little bit, or I have to check, is that there exists a commutative diagram. So S tensor HMIR. So there's a natural map to HMSIS, right? So because this is just the base change. And here I could apply, I have a splitting from S to R, which is an R linear map. So that induces a map from HMIS to HMIR. Right, so this is, I apply HMI of the splitting. Okay, but here I have an obvious map, right? Because I could apply phi tensor with the identity map. Okay, so that phi sends S to R and then this. Right, so the only thing that I have to check is this diagram commutes. Okay. And now let's just use this diagram to prove the claim. So say I have, so the image of, right? So what I want to do, so let me just, maybe it's better to just mark this on the picture. So I have eta inside here, and I also have this capital N here. I wanted to show eta is inside N. So that's my goal, right? So what I'm going to do, I'm going to look at one tensor eta inside here, right? So so that's gonna map to well, let me just get the image of one tensor eta here. Right, so that's just the image of eta under this natural map from HMIR to HMIS, right? But if I apply this map here, or apply this map downstairs, I get back to eta because phi sending 1 to 1. So I get back to eta. Okay. And so now, so suppose the image of one tensor eta. So our assumption is that after you map everything to HMI S, the image of eta is in the S span of the image of n. So what does that mean is that the image of one tensor eta is a summation Si tensor Si times the image one tensor eta I, where Si inside S and eta I is inside n. That's precisely our assumption. Okay? But now just apply the HMI phi, okay, to, well, this is star, right, and use the commutative diagram, right? So we get, of course, the left-hand side, I just get back eta, right? So what about this? Okay, so I apply HMI phi, but that's, well, it's S linear, so, well, I can, so this is just, you know, image of, I can pull this, like, this is image of Si tensor eta I. So I apply this HMI phi, that's the same as I apply phi tensor ID to Si tensor eta I. So what I'm going to get is that we get eta equals to the summation of phi of Si tensor eta I. Okay? But that's inside n, because each eta I is inside n. So, and phi of Si is, I don't really care, it's some element inside R. Okay? So if you think about it, it looks like I'm doing nothing, but if you think a little bit, right, so the sort of, there's a subtlety that lies behind is because this diagram commutes, because the information I need in this HMIS, actually I can do it inside S tensor HMIR, but that here after apply splitting, everything is obvious. So it's just okay. So I have this claim. It says if I have a split map and I have a module and if I have an element, if the element is inside the span after, after I do on the HMI of the target ring, and then I can conclude that eta is inside HMIR before I for the base ring. Okay, and so now now I want to go back to the proof of this theorem. So if F split implies the Frobenius is injective on HMIR modulo any F stable submodule. So now suppose n inside HMIR is F stable such that the Frobenius on HMIR modulo n is not injective. Right? So, but then what does that mean? So then there exists eta not contained inside capital N, such that after apply the Frobenius is inside N. Right, so it's just the definition. So I let NE be the R span of FE of N. Right, so this is, again, FE of capital N is the image of N under the eth iterates of the natural Frobenius action. Right, so it's not necessarily, so this itself is not necessarily an R module, but I look at the R span. So this is going to be N. Right, so I guess if you like this notation, I should FEN by R. So I really mean this. Okay. We have a descending chain. So N obviously contained inside N1 obviously contains N2. right? So here I'm using that n is F stable because, well, for example, let's just look at here. So why is that? Because n1 is the R span of f of n, but n is F stable, so Fn is contained inside n. So the R span of f of n is also contained inside n because n is an R mod. Okay, so that's, and then we iterate this. You got a descending chain. So this chain stabilizes. Right, because HMIR is Artinian. Right, so what does that mean? That there exists E very, very large, such that NE equals to NE plus 1. Okay, but since f of eta is inside n, right? So what I'm gonna get is that, you know, if I iterate, f square of eta is gonna be inside n1, So basically, I'm just gonna put its parentheses here. So if I apply the Frobenius e plus 1 time to eta, well, that's always gonna length inside ne. Right? But now ne equals to ne plus 1. So what I'm gonna get is that there exists E sufficiently large such that Fe plus 1 of eta is contained inside ne plus 1. Okay, so that's what I conclude from this chain. Okay, and now we apply the claim to the E plus 1 Frobenius. Right, so remember this is a ring homomorphism that is split. Right, so this is compatible with the assumption in our claim. Our claim, I have a ring homomorphism which is split, and I can apply whatever, you know, this conclusion. And so here is exactly, I'm going to apply the claim to this ring homomorphism, and the R span. So I mean, if you think about it, so Fe plus 1 eta inside Ne plus 1 is precisely saying that the image of eta is in the R span of the image of n under the HMIR, the E plus 1 Frobenius HMIR. Right, so this is precisely what is this claim is saying. And now you can apply the conclusion of the scheme, the claim. So claim implies that eta is inside n. Contradiction. Okay, so that's the proof of the theorem that well, I'm gonna using this Frobenius is split here. So that's the proof that if R is F split, then for any, let me just go back. It's a little bit. Yeah, I'm basically proving this theorem. Right. So if R is F split, then for all F stable submodule, the Frobenius act, the induced natural Frobenius action on HMIR quotient by this F stable submodule is injective. Okay, so now finally let me prove the part 2 of the theorem. Right, so let me recall. So the thing is that R mod X is F split implies R is F injective. This is the thing I wanted to prove. So the point I prove carefully this theorem that I stated here is because if you use this theorem, then the proof of case 2 of the deformation question is basically you can run the same argument as we did in the Cole-Macaulay case. So that's really so the original proof of Hurichi, Miller, and Shimamoto is slightly different, but they prove something slightly more general that I don't want to state it here, but the main corollary is that the F split implies F injective, and in this case, we can just apply the above theorem to give a sort of simpler argument. Okay? But their result is slightly more general, and they also use my theorem, but they carried the proof to some slight general context. Okay? So I encourage you to read their paper if you are interested in this topic. But anyway, let me just quickly finish this. So the strategy is the same as in the CM case. Okay, so we have this commutative diagram. So here's the natural Frobenius, here's the natural Frobenius. Here is the natural Frobenius post-composed with x to the p minus 1. Okay, and so now it induces a map, right? So I want to look at the ith local cohomology now. So I have HMIR multiplication by x, HMIR, and here I want to put HMI minus 1 of R mod x, but of course, if I put this guy, I don't have a, it's not exact. It's not, this is not the kernel. The kernel is this one really, this one modulo the image of HMI minus 1 of R. Okay, so I'm just gonna keep this, whatever thing here, and this I don't really care, just keep going. This is the natural Frobenius, this is the natural Frobenius, and here I have x to the p minus 1 times capital F. Okay, so now this diagram commutes, right? So it's slightly more complicated than the Cole-Macaulay case because the left-hand side is not really the local cohomology of R mod x, it's the local cohomology of R mod x mod the image of whatever coming from the previous, like HMI minus 1 of R. Right, but the point is that, so the image of HMI minus 1 of R, I don't know what it is, but at least I know it is F stable. Okay. Oops, just F stable. All right. Therefore, by theorem that I just proved, since remember we are assuming R mod x is F split, we are not merely assuming it is F injective, we are assuming it is F split. So the previous theorem says precisely that the induced Frobenius action on HMI R mod x modulo quotient any F stable submodule is injective. So this is injective. The left-hand side F is injective. Okay, and now use the same diagram chasing to show x to the p minus 1 times capital F is injective. HMI. Okay, so let me just I'm running out of time, so let me just sketch this very quickly on this picture. So again, you pick something in the kernel. Suppose you have something in the kernel. You can always assume this thing simultaneously lies in the socle because you can just replace it by a multiple. But then after you assume this is in the socle, it maps to 0 because this map is multiplication by x, right? But once you know this maps to 0, it's coming from something inside here. Right? So this eta is really coming from left-hand side. And this eta, whatever this module is, I don't really care what is this module, but it's something inside here. And it has an image. Let's say it's theta. I'm just using the same notation, actually. But now theta goes to 0, which means, well, I mean, by the commutativity of this diagram, but then you have this injectivity here. So that implies theta equal to 0, but eta maps to 0, and this left-hand side map here, this map here is injective. That's what we conclude from the F-split property. So eta is 0. So it's, if you think a little bit, this is the same diagram tracing as in the Cohen-Macaulay case, except we sort of modify slightly what's going to happening on the left and using the slightly stronger result that, you know, I mean, F-split implies this stronger thing that quotienting by any F-stable submodule remains the injectivity of the Frobenius. Okay, so this is the main theorem that I want to report. And okay, so I think I will stop here. Thank you for your attention.
Thank you very much, Linquan. We